right? Impedance looking in here, right, is going to be 75 ohm, right? Because what the problem asked for is that it actually wanted the circuit to design a circuit where the Rin was 75 ohm.
Yeah, that's okay.
Right? And then I also said that it was driven by the source impedance of 75 ohm. Right? That's the way the problem was set up. Okay. So actually, if you look at the gain from, if this is Vin, okay, the gain is actually to half times GMRC rather than just GMRC, because GMRC, the gain is from the GMRC is from the emitter node to the output collector node is the GMRC times the voltage here. But now what I have is I have actually RS of 75 ohm, impedance looking in of 75 ohm here. So if I apply V in here, what is the voltage here?
Sorry, what was it?
See, if I apply V in here, and then I have source resistance 75 ohm, and then resistance looking in here, it's 75 ohm. Okay, then what is the voltage here with respect to V in? Half, right? Because it's a voltage divider between 75 ohm and 75 ohm, right? And so this right here is going to be just half V in. So emitter voltage is actually half V in. Okay, and of course from emitter to the collector, the gain is GM times RC.
So you're saying that this input looking into there is not the total input?
Well, it's the total.
Total.
Yeah, but we have designed such that it's 75 ohm.
Okay.
Right? So we have designed such that impedance looking in here is 75 ohm. Right?
Yeah.
And then of course, this is going to be short for the signal process,
For the
normal operation.
Yeah.
Right? And so we just have a RS and input resistance which is 75 ohm.
Right, but we don't think about RDs?
RE? Oh, but RE is part of the 75 ohm.
Right, but wouldn't it have to be like crazy high since they're in
Yeah,
parallel?
that's right. They should be anyway.
Yeah.
Well, because you want to have this thing high for, make sure that the bias is stable.
Well, I thought the biasing for that would only usually be around like 200, 300 ohms.
This one?
Yeah. Oh, that's only for the BJTs?
No, this is okay. Oh, this was a MOSFET. Was it MOSFET circuit or
Yeah.
BJT circuit?
This is
It's-
NPN.
No, it was an NPN, right?
Yeah.
No, sorry, Heidi. But they're the same anyway, right? So it's
I know it's supposed to be less than RC and
yeah. So I mean, typically this should be like 100 kilo ohms or 500 ohms or something. It's higher. Okay. But the bottom line is that whenever you do the design, you have to make sure that impedance looking in here, right?
yeah.
Is going to be basically you want to set up so that it's 1 over GM parallel with RE, right?
Okay.
And so this thing has to be much bigger than 1 over GM, which is normally the case.
Right.
This is more like either like 26 to 50 ohm kind of.
Yeah. So it'll just be around that.
Yeah. So
Yeah.
so this has to be part of the design so that it's 75 ohm. Right? And so that's taken care of. And so bottom line is that impedance here, I said design it for 75 ohm. Right? And so impedance looking in is 75 ohm. And so if I apply voltage here, then up to here this will be half because they are same, right? The voltage divider between 75 ohm and another 75 ohm. Right? So this is going to be half V. And of course now you are at the emitter node. So for the common base amplifier, when you have the voltage gain from the emitter node to the collector node is GM times RC. Okay, so this you get this, right? And of course, what is this? This is equal to half times IC over VT times RC. Right? And so this right here, this is a VRC.
Okay.
That's a VRC. And of course, the question is, if you want to do it maximum, what should this be? So if you want to do maximum, right? What happens? The maximum voltage that you can have, maximum voltage gain you can have is what? VCC. So what happens if you make this drop across this? The VRC is a voltage drop across this resistor, right?
Yeah.
If you make this thing really large, what happens? How large can I make? Right. So this is right here. This voltage is the VRE, right? How low can I go here?
Oh, I remember, cause it has to be,
So the how low can I make the output voltage be? Because I have to make sure the transistor stays forward active, right?
VCC minus VCC minus
Right. So this point can go as low as VRE plus the VC set, right? So this point right here, so this transistor, the VCE of this transistor can go as low as VC set, right? Because if you go lower than that, then you are going to in the saturation region, right? And so that means the V out can go as low as VRE plus VCE set. Okay, and so that's where this comes from. And of course, VCC minus the lowest point you can have. Okay, that's going to give you it's a maximum VRC you can have.
okay.
That's the maximum VRC you can have. But actually, there's a little more to it because this problem said, I believe it said, the output voltage swing has to be plus minus
It says at least 3 volts.
3 volt peak to peak, right?
Yes.
It said the peak to peak is 3 volt, right? So what that means is that I have to set it up such that the VC set plus, right, VRE has to be, it cannot be, this thing cannot be greater. So what that means is that for me to support peak-to-peak voltage of 3 volt, right? Where should I need this? Where do I need to set this voltage to be if I want to support output voltage to swing from plus minus, so it's just 3 volts. So that means your AC signal is a peak-to-peak signal at this node, right? If you look at the voltage, it's collector voltage, and so I'm going to have AC output going plus 1.5 volt and minus 1.5 volt. Right?
Yeah.
So that's how much I'll be able to swing, where I need to be able to swing. And then, I have to make sure that the circuit at this point is greater than VRE plus VC set.
Okay.
If I want to satisfy this.
To stay in the operator.
Yeah, to make sure that the circuit is in the forward active region of operation.
Okay.
And so what does that say? It says that the VRE plus VC set, it also says that VRE plus VC set has to be less than, so what you want is when you build an amplifier like this, right? What you need, depending on how you set, right? Suppose if I set VC to be, so VCC was what, 5 volt for the problem?
Oh, yeah.
5 volt. So if I set VC to be, say, 4 volt, okay? Would I get the full swing? No. Why not? Right? Because what happens if this is 4 volt and if I go 1.5 volt, then what happens? This will be at 5.5 volt, and so I'm going to run into saturation, right? Because this voltage here cannot go above 5 volt. Okay, and so if you want to support this, this thing has to be. What should this voltage be?
3.5.
At least 3.5 volt. Okay, and so the 3.5 volt. So then you also have to support this thing, which will be 1.5 volt. So if you subtract 1.5 volt to this, and this is 2 volt. And so you have to make sure, right? You have to make sure that the VRE, so this, the VRE plus VC set, right, has to be greater than, well, you have to make sure that VRE plus VC set is less than 2 volt. Otherwise, you're going to run into the transistor saturation. Okay. Because if you set your gain to be this, do you think you will be able to meet the swing requirement? Because the way that I have set up right now is if I set the maximum gain to be this, okay, so that means the DC voltage drop is actually so let's go back to this example, right? Suppose I set the VRE plus VC set, right, is equal to 2 volt. Okay, right at the edge. Okay. If I set that equal to 2 volt, then what is this VCC minus VC set minus VRE? It's going to be 3 volt, right? So 3 volts, so that means your DC bias point is what? Your DC bias point is at, your collector voltage is going to be at, your collector volt, so you're going to drop 3 volt across here, right? So that means your DC voltage here is going to be 2 volt, right? 2 volt. So if this point is 2 volt, can I have any swing? Because I need to make sure that VRE plus VC set, right, has to be less, has to be, well, this voltage here has to be greater than 2 volt that I have started out with, right? So if I were to have any kind of swing, so if this is at 2 volt, and if I have a swing like this, what happens to at this portion, what happens to the voltage, collector voltage? It's going to go below 2 volt, right? So that means the transistor will saturate, right? So then this circuit is not going to be in amplification stage. Okay. And so what actually, what that means is that you have to decrease the gain. You have to actually go by roughly another factor of half is what you need. So that instead of centering your design at this point, you're going to be instead of centering the voltage at 2 volt, what you like to do is you like to center this thing at, like we said, around 3.5 volt, right? Because you cannot really go much lower than that. And so that means you have to go up by roughly another half. And so this actually requires iteration, okay? Because of course this also depends on what the VRE is. right? But did I specify what the VRE should be? I might have said VRE should be something.
It says set the voltage drop across the emitter degeneration
Should be
resistor to
1
1
volt.
volt.
Yeah, so, right? So then, what that says is that, yeah, so, so what that says is, so if this is 1 volt, so that the maximum that I can go down here, 1.3, is 1.3. Right? So that's, so the maximum that I can go down to is 1.3, but now I need to support, right? So what that means is that, what that means is that if I were to look at the output voltage, I want to set such that VC here, right? Because the whole idea is that if you want to maximize the gain, what has happened? The IC times RC, right? I mean, the gain is just half times VRC over VT, right? So what you want to do is you want to maximize the VRC, okay? And while satisfying the voltage swing, right? And so the maximum, the VRC or that you can have, right? This VCC is VC is VCC minus the VRC. Okay, this is the collective DC voltage is going to be VCC minus the voltage drop across the RC, so it's minus VRC. Right? And so what we want to do is we want to set it up such that when we have the maximum swing, right, the lowest point right here, that has to be the VRE plus the VC set, as we talked about, right? Because when the output swing goes to lowest, right, the lowest point that this code can go is that VRE plus the VC set, right? And of course, the lowest point will occur on the downward swing of your output signal. And so we want this thing to be 1.5 volt, and we want this thing to be 1.5 volt. Or we want this VC here to be what? So we know the VRE plus VC set is 1 volt, this is given, plus 0.3 volt, plus 1.5. So this whole thing is what? 2.8 volt. Okay. So that means what is a VRC? VRC has to be 5 volt minus 2.8 volt, which is the VC. So that's 2.2 volt. And so the maximum gain that you will be able to get from this circuit is satisfying all these requirements will be half times the 2.2 volt divided by 26 volt, or 0.026. Okay. So, and then of course, this expression here, right? This is valid if you don't have any output swing requirement, right? If there is really, if you, this is really pushing all the way down, right? And it's at the lowest point, but the thing is that if you have any little bit of downward swing, the transistor is going to be in saturation, right? And so if you wanted to, accommodate this headroom, you have to push this thing up, right? And of course that means the gain goes down. And of course here, now if I set this thing to be 2.8 volt, what is the highest point? Highest point will be 4.3 volt, right? Which is okay, right? Because as long as this is less than 5 volt, then we'll be able to have output swing. But if this thing was actually above the 5.5 volt, then that would be a problem. Does this make sense? Because I mean, at the end, it comes from here, right? It's the gain is VRC over VT, and then of course you have factor of half because you're trying to do the matching. That the input resistance is 75 ohm and source resistance is 75.
Was VCE set given as 0.3?
Yeah. That's right. Normally it'll be given to you, or you know sometimes you know I think another definition is when you know BC or when the VCB becomes 0, right? These are other definitions sometimes the book uses, but it's VC set is really the right way to look at it. Yeah, so that'll be given. How are you doing at the time?
40 minutes. 4:20.
Okay. Okay, so. Any other questions? Yeah. How do you guys feel? So what answers?
So we're gonna need the answers to the test, how to do that.
But you know, spend time to make the you know those you know the summary sheets that I'm doing, right? That's actually a good way to study. Yeah. Right.
Oh, when will homework 14 solutions be posted?
Yeah, I think I'll try to get it done today.
Okay.
Yeah, today or tomorrow morning.
And the bonus homework is replacing the
One of the
homework.
homeworks. One of the
That's due on the exam.
This is just kind of like curiosity. Do you have like a great histogram for like the class overall?
that's something that I keep it secret. But I mean,
So
I
you
do.
do have it.
No, but I think most of the undergraduate, you know, at least my understanding is that most of the undergraduate, you know, the core classes, the average is roughly, I think, the average GPA, I think it's like 2.7.
Wait, really?
Maybe around that you know, that number is what I think all the core classes are like. Yeah.
And will there be a curve?
At least up till now, I don't think there is need to be. You know, I remember going through the midterm grade, and I was looking at how you guys did the midterm exam. I don't,
There's always need for.
because I don't think there was actually need for it at all, which I thought was really good. Because I don't remember the average of the midterm. What's the midterm average?
78.
Yeah. So it's seven. What is 2.7? Is that B minus?
Yeah.
Yeah. Just okay. So yeah, maybe. But anyway, so I mean, the bottom line is supposed to be something on that order. It's consistent with all other classes.
And we have 4 sheets, and each sheet is front and back, right? So it's 8 sheets total.
Eight pages.
Yeah.
So for frequency response,
Yeah.
we're focusing on, one of the most things to take away from it would be the Bode graphs and the poles and zeros.
I think think about what I talked about in the class, in the lectures, right? And also the problems that I was solving, right? I think one of the things that I really like you guys to be able to understand is the Miller effect.
Right, which would just be the current.
I think the Miller effect is very important. But the other thing is also, I need you to understand, why you have these capacitances in the transistors, right? I mean, number one, that's the first place, right? Why does it, at high frequencies, why does the the circuit behavior deviate from the mid-band response that we talked about? Because that comes from the transistor parasitics, right? And so what transistor parasitics do we have? We have base emitter junction capacitance or gate to source capacitance, which are equivalent. And we have a gate to drain and this gate to or base to collector capacitance, which are equivalent, right? Or they play the same role, right? And so, and then of course the thing that makes the CGD bad, or the gate to drain or base to collector capacitance bad, is because that's
Not easily assembled.
yeah, right, because it couples the output signal to the input. And so the analysis becomes messy. And so then you have this Miller, and then of course it's called Miller, right? And Miller effect. And so we use the Miller theorem to simplify the analysis. Right? So that's actually a pretty powerful theorem. Okay. Of course, the other piece is that one of the real bad part about this Miller effect is that if you look at the capacitance looking from the input, when you have gain, what happens to the capacitance? Capacitance actually looks bigger than actual CGD, right? Because the capacitance that you're looking from the input becomes essentially it's 1 minus A times the capacitance, right? And then when the minus, gain is minus, which is the case for common emitter or common source amplifier, then it becomes 1 plus the magnitude of the gain times the Miller capacitor, or the overlap, this coupling capacitor, right? Or the capacitance between gate and the drain, or base and collector. Right? And so the capacitance actually looks bigger, right? And then so we talked about this Miller multiplication of the capacitance. So the capacitance looks bigger, and of course, if the capacitance looks bigger, what happens to the frequency response? Your gain will roll off faster, earlier, right? At lower frequency than what you would have just expected from the capacitance, right? And so that's the Miller capacitance or Miller effect. And so that's usually one of the dominant reasons, one of the key reasons why the frequency response of the circuit degrades. And of course, the other one is output, right? Because at the output you may have capacitive load. Okay, so there's another pole there. Right? So typically there are two poles, right?
Input and output.
Input and output. And the input pole is associated with the this whatever the resistance that you have at the input plus the this Miller capacitance. And then output is typically determined by your load resistance and the load capacitance. Right, so if you have so if you have and let's be simple. We have a common emitter amplifier like this, and then let's keep everything the same. Okay, let's start with RC, and then there's some CL, and then you have let's say and then we have say coupling capacitor. Right. And so if you look at this gain of this circuit, as we talked about, right, if you look at the magnitude, V out over V in, and then this is omega, the frequency, right? And we said that the gain would look something like this, right? And then of course, this right here, this guy is associated with the poles and the zeros, right? Associated with these guys. And so there is omega L. So this actually has to do with the bypass and the coupling caps. And this guy right here is associated with the transistor. And of course, at high frequencies, this becomes all short. This becomes short. So if you draw the small signal model for the high frequency analysis, it's going to be just transistor. This will be R pi. And so this is going to be AC grounded. This is bypass cap, right? This is AC grounded. And then I have GM P pi, and then I have plus minus P pi. And then I have C pi, right? And then I have C mu. base collector capacitance. And then I have RC and CL. Right? And so this is gonna be the P in. And this right here. This is P out.
So what is CL?
That's the load capacitance.
Right, but wouldn't it still be affected by, oh, that's input.
Yeah.
Okay, never mind.
Cool. And so the way that we do this is the first thing, okay, so now question is, how to deal with this CMU, right? So it's a Miller capacitance. And so the way that we deal with it is by using Miller theorem, right? And so the way that Miller theorem works is that the first thing you do is you compute the gain between, across this capacitor, right? So this is the gain between these two nodes, right? Which happens to be just the V out over V in when just midband gain, right? Because once you take this out, right? If you put V in, what happens? V in basically goes across the V pi, right? And then the output is going to be the GM V pi times RC. And of course in parallel with the CL, but what we assumed is that that doesn't happen. The pole, we assume that that pole occurs at a higher frequency than the pole associated with this thing. So if we neglect effects of this, then we can say that the voltage gain that we're talking about from between these 2 points here is just nothing more than GMRC times minus, right? That's the voltage gain between those two nodes, between here and there. Which two? The voltage across the collector and base, because this is the C mu here. I'm computing the gain without the C mu. Okay. And so if I compute the gain between collector and base, that's just GMRC for this amplifier. Okay. So it's minus GMRC. And so if you apply the Miller theorem, what happens? Now we put the C mu back in here, and then we apply the Miller's theorem. Okay. And then when I apply the Miller's theorem, what happens to the input network? I have this right here, R pi, I have C pi, and then I have CF. And then I have, on the output network, I have, I think GF1 and then GMV pi. I have RC, and then I have CL, and then I have also CF2. And then I have plus minus P. And so what is the ZF1? ZF1 is equal to Z mu divided by 1 minus A, right? And ZF2 is equal to actually Z mu times 1 over, I think 1 over A. Right? And of course we know that A is equal to minus GMRC, so this is really Z mu over 1 plus GMRC. And ZF2, which is equal to Z mu over 1 plus 1 over GMRC. That's the gain, right? So this right here is the and so what is this? This Z mu we know is equal to 1 over C mu omega j times 1 plus GM RC is going to be C mu. Well, this is ZF1 is going to be 1 over C mu, because Z mu is 1 over C mu omega j, and so I have this 1 plus GMRC there, and so this is actually equal to ZF1. And of course, ZF2 is equal to 1 over C mu omega j times 1 plus 1 over GMRC. And so these are capacitors, right? And then if you look at this, right, the impedance of this GF1 is lower than the impedance of C mu by a factor of 1 plus GMRC. Or the gain of this amplifier, well, not the gain, but the impedance has, or the capacitance has now gone up by a factor of 1 plus GMRC. Because it's 1 plus GMRC times C mu omega j. And so the Cx that I talk about is equal to actually C mu times 1 plus GMRC. This is the middle multiplied capacitance, so which is, this is equal to 1 over Cx omega j. And of course this right here in the lecture I called it as 1 over Cy omega j, where Cy is equal to C mu times 1 plus 1 over GMRC, and typically if the gain is high, then this is roughly equal to C mu. Right? And so on the input side, the capacitance that you look actually has been multiplied by a factor of 1 plus GMRC. And so that's a very important thing to remember. That's really why you care about this analysis, because this feedback capacitance between the output and the input, this capacitance always look bigger than actual value. So even if you have a small capacitance, at the input it will look much bigger because you have that feedback. Okay, so that's why you care about this. That's why this is so important, because capacitance look bigger. And so that's why you cannot neglect it, right? And so that's why you need to actually use this Miller's theorem to analyze it. Okay. And so now we have this guy. And so if you look at all the capacitances on the input side, what do I have? On the input side, I have so I have Cx. So this is Cx, right? And then I have here, this is C mu. Cy. Huh? What? C which is equal to Cy, right? Which is roughly equal to C mu, and there's a Z pi here. This is really C pi, right? And so if you look at the whole input network, what's the time constant? So I have R pi in parallel with C pi plus C mu. And so the time constant associated with the input network is going to be just
Wait, C mu or Cx?
well, this is Cx. Cx. Okay. So of course now I have to do something here. Let me I think I did something wrong here. So what I should have is I should have some RS here. Okay, so that I have let me put some source resistance associated with the input. Okay, and so then of course I have this RS here. Okay, and then so if you look at the poles. What are the poles that I have at the input? Well, the pole that I have at the input is going to be basically this capacitance, right? And the resistance associated with the rest of the network. Okay. And so that pole is going to be the C pi plus Cx times the R pi in parallel with the RS. And at the output, what are the poles that I have? I have just RL And it's time, RC time constant, so the capacitance that I have will be CL plus CY. And of course, if I have output resistance R0 here,
It would include in parallel with RC.
so then RL will be in parallel with. Okay, and so if you look at the frequency response of this circuit, it'll be 1 plus S over omega 1, right, times 1 over 1 plus S over omega 2. And where omega 1, so this is going to be 1 over omega 1, and this is going to be 1 over.
So when we were doing the BJT problems early in the year, we were always in the lower operating region, right?
This is where you are.
Okay.
We are always here.
Alright. But with the capacitors included for accompanying
Which capacitors?
the
These capacitors?
yeah, those two.
Yeah.
In the operating region, those two wouldn't.
This is where we are.
Those two wouldn't be in effect since we're in the.
That's right. That's right. They will be already shorted out, right?
Yeah.
And of course, it's right here is when they are effective now.
Yeah, so we designed it in low frequency, operating.
Okay. Because of course, we have to add these things because we're trying to do the biasing,
Yeah.
right? But if you don't have to do the biasing, then if you don't have this, the response. If you don't have the coupling capacitors, your response will be more like this.
Yeah.
Instead of looking like this.
Professor?
Yeah.
What is that S?
S.
J
That's all J omega,
J omega, right?
right? So S is going to be.
And what are those two values they represent? The
Which
one
one? Omega 1 and omega 2? These are the poles.
The 1 over the 1 plus S over omega 1.
So that's
Okay.
that's pole associated with this one, and
Okay.
pole associated with this one. So if you actually look at the frequency response of this, the way this works. Okay, suppose normally it depends, but if this one is the dominant, right? Because actually the other thing that I talked about is that usually one is much larger than the other one, right? So there's a dominant pole, and then typically it's this one that dominates over this one. Okay? If that's the case, and it could be otherwise too, right? But let's assume that this dominates over the other one. So what happens is that this is omega h, right? This is going to be roughly equal to omega 1 if this one is the dominant. Okay? And so in reality, what happens is that it would go down like this, and then when you hit omega 2, it will go down faster. So this could be omega 2 here, in reality. But the thing is that you don't really care. Okay? A lot of times you don't really care because, you just want to make sure that you are here, right? You want to see where the first one is. But actually you do care later on, but at least for
It's
the time being.
high resolution.
Yeah.
Because for the 1 plus, every time you hit a pole, then it increases or decreases by 20 decibels or something like that. Okay, so that
That's
makes
exactly
sense.
the same thing.
Okay.
Yeah.
And what was omega L again?
Omega L? Oh, this is the low frequency.
Okay.
Cutoff frequency, which is different. We talked about this, and it depends on the time constant associated with these two capacitors,
Okay.
the bypass caps and coupling.
Okay, so that's related to the capacitors at low frequency, and then that's related to the.
Transistor capacitors. So
Okay.
these are related to the transistor capacitors.
Okay.
These are related to the bypass and coupling capacitors.
Professor,
Yeah.
quick question.
Sure.
So why did you do 1 over 1 plus S over omega 1 times 1 over that as well? Like, why did you multiply those two?
Yeah. So so this is how you do the so what you're saying is that you have a frequency response,